In section 2.4, we're going to work with what are called imaginary numbers, or complex numbers. Those involve mixing real and imaginary numbers. They generally stem from trying to take the square root. So let's, for example, look at x squared equals 16. Many people, when asked about this and what the solution might be, would say, oh, x is 4, because 4 squared makes 16. However, it's important to note that putting in a negative 4 would also work in for x, because a negative times a negative would make a positive. To solve this, we might say we want to cancel out the square power here, so we're going to square root both sides. That would mean x equals plus or minus 4. Down here we have this note that says, remember, when you take the square root, the answer is always a positive and a negative number. That's to say plus or minus 4 in this example. But what happens over here when someone says x squared equals 9? What might x be? Well, to cancel out the squared, we still could take the square root. And it leaves us with x. We'd remember to put our plus and minus. But the square root of negative 9, in the past, we would say there's no solution. We can't get some number times itself, even 3 times 3, or negative 3 times negative 3. They'll always come out to a positive 9. That's why we normally would say there's no solution. However, with this chapter, or this section, we're going to be noting that if we ever have a negative under the square root, that will involve an imaginary number. And we're going to call that imaginary number I. It will stand for the square root of negative 1. So we could write, if we make a factor tree here, negative 1 times 9. We could take the square root of negative 1 and the square root of 9, and that would multiply to the square root of negative 9. We all know the square root of 9 is 3, so we could say, oh yeah, it would be plus or minus 3. But when we have the square root of negative 1, we're going to call it I. So I would actually write it like this. Remember, I is an imaginary number, something unique to think about, but we'll use that to represent any time we see the square root of negative 1. For this study tip, they want to mention that if you were given x squared equals 16 again, one way you could solve it, like you have been in section 2.3, is to subtract 16 from both sides, and then think about factoring that. Well, x times x would make x squared, and 4 times negative 4 would make 16. So my zeros, x would be negative 4 for this one, and x would be positive 4. Those would give me the same answers as I got in the first part of example 1. For the triets, you could do the same thing here. I'll try B for you. If you took the square root of both sides, you'd get your x. We don't want to forget that plus minus. But now, when we take the square root of negative 72, we are going to be hoping that you'll think of what are called these factor trees. Maybe you remember them from, say, middle school. But if we have negative 72 in here, we know we can take out the negative. We'd have the square root of negative 1 times. We want to think of what multiplies to 72. And sometimes it's important to think of numbers that are perfect squares. For example, 4s are good, 16 is great, 25, 9, 36, any number that's a perfect square. I happen to know that this 36, if you take that times 2, that will make 72. So 36 times 2 makes 72. Those are called factors. Now, when solving this, I have x equals plus or minus. I know the square root of 36 is 6, so I'll put that out front here. We are going to treat, remember, every time we see square root of negative 1, we are going to write it as I, because it's an imaginary number. You cannot square root a negative number. So this will become an I, and then that square root of 2, we can't reduce it any further, and he's stuck under there, so that would be our final answer for the triad part B. To summarize complex numbers or imaginary numbers, here we have our reminder that anytime we have the square root of a negative 1, we're going to refer to it or substitute in the I. So they call complex numbers like a BI or a number times I. So for example, 7i would be referred to as a complex number. Now remember, that'd be the same as writing 7 square root of negative 1, because I and the square root of negative 1 can be substituted for each other. We will generally write it, though, as the I. That would simplify it more. The mix of real and imaginary numbers are what we call complex numbers. They're complex because they mix the real numbers we're used to with the imaginary numbers. So here you'll see our imaginary number component with that bi, and we would have our a, which is just a regular number. So for example, this is what we would call a complex number. Now, when we try example 2, they're basically going to have us adding and subtracting complex numbers. This actually isn't terribly scary at all. Remember to just combine the real parts with the real parts. So all the real parts are the normal numbers you're used to, and the imaginary parts. So what that means is, if we look over here for the real parts of the equation, so they want to sum, they want to add up. So I'd have a real part here in 4 and negative 11. Those are the normal numbers we're used to. But the imaginary part, we'll put in orange here, we'd have negative 7i and 9i. Now, when they say the sum, we'd have 4 minus 7i plus negative 11 plus 9i. I'm using the parentheses just to be careful that I don't miss any sign changes, but if I want to combine the real parts, so I'm going to combine the real parts here. What is 4 plus negative 11? I'd get negative 7. If I combine the imaginary parts, I would get my negative 7i, don't forget the sign, plus 9i. So basically 9i minus 7i would give me 2i. This is your final answer. The math behind it is not too crazy. It's really kind of like pretending your I is an X value. It's a different kind of term. The one thing I do want you to watch out for is whenever they want the difference. That would mean taking 6 plus 8i and subtracting 2 minus 5i. That subtraction sign can cause lots of headaches. One thing you could do is change this subtraction sign to a plus and then change all the signs afterwards. You might have heard keep, change, change. You might have heard change the subtraction to addition and add the opposite. If I do that, I would combine my real parts now, and I would have 6 plus negative 2i, which would make 4. And I don't think that would confuse people. If you said take 6 minus 2, no big deal. But when I want my imaginary parts, and I have 8i here, and I'm going to plus 5i, I'd have my 13i. But had I not paid attention to subtraction and not wrote it out again like this, I'd have 8i, and I'd say, oh yes, subtract 5i. I might think that the answer is 3i. It's not, because I want to take 8i and subtract a negative, which means you're adding. So our final answer is 4 plus 13i. You can try the try-its for this example too, and check the packet for your answer key. Keeping in mind that we know square root of negative 1 is I, we'll use that, and now we're going to find times where we're going to be multiplying. So we added and subtracted in example 2. Now we're going to multiply. Nothing really changes here, so I'm going to distribute this negative 2.5i times 8, and I'm going to distribute negative 2.5i times negative 9i. When I do that, I get negative 20i plus, because a negative times a negative, 9 times 2.5 would make 22.5. And I have I squared. So I have I times I, and just like x times x, it would make I squared. If I would take up here, and I remember that negative, or square root of negative 1 is I, if I square both of these, when you square and square root, it's kind of like tie your shoe and untie your shoe. You're right back to where you started. So someone has negative 1, then they decide to square it, square root it, and then they decide to square it. They basically cancel those out. So what we're looking at is negative 1 is going to be replaceable every time we see I squared. So I've wrote that down here in your common error and what to remember. That means every time we see I squared, we're going to put in or substitute negative 1. So I would have negative 20i plus, and we don't want to rewrite this I with square root of negative 1. We prefer to leave it as I. I'll have 22.5, but instead of I squared, I'm going to substitute negative 1. That means multiply by negative 1. So you'll see this common error down here. You want to actually replace that I squared with negative 1. By doing so, I get negative 20I, and positive times a negative 1 would be a negative 22.5. And this would be your final answer. Looking at B, we're still multiplying, but hooray, we get to do the distribution process, or the box and diamond, or the box method, or the rainbow method. And we'll try this here. So we would have 3 times 3 would be 9. And then I would have 3 times 2I would be 6I, so plus 6I. Then I would have negative 2 times negative 2I times positive 3 is a negative 6I. And finally, I'd have negative 2I times a positive 2I is a negative 4I squared. We can see these middle terms. They're going to cancel because 6I take away 6I will go away. So I'm left with 9 minus 4I squared. But we are going to replace, every time you see an I squared, you're going to replace that with negative 1. So I'd put in negative 1 down here in place of my I squared. 9 minus 4 will carry down. And now, negative 4 times negative 1 is a positive 4. So I'd have 9 plus 4, which equals 13. Crazy enough, all that I business in the beginning ends up being just 13. Go ahead and try the triads. A few fraction yuckiness down there. Keep in mind, if you took 2/5 times 5/2, that'd be 10 over 10, because you just multiply straight across. So it would just basically be 1. Don't let those fractions freak you out there. And of course, also be watching for anytime you see I squared, replace it with a negative 1 or substitute that in and multiply your answer that had I squared with it by negative 1.